This is a useful quantity when we consider a process which takes place when a system is in mechanical and thermal contact. With reservoir. So the volume of the system can adjust to maintain pressure equilibrium with the reservoir. And then we can consider what I'll call the available work. That means, well, if we change parameters like temperature and pressure, there's going to be some work done because there's heat flow into or out of the system to maintain thermal equilibrium, or there's an adjustment in the volume of the system to maintain pressure equilibrium. So if we subtract that away, what's left is the available work, and the change in the Gibbs free energy keeps track of that. The Gibbs free energy we can express as Helmholtz free energy plus pressure times volume. In other words, internal energy minus temperature times entropy plus pressure times volume. And dG then can be expressed using the appropriate thermodynamic identity as minus sigma d tau plus v dp plus mu dn. Now we saw that if there's a single species of particles, we can write the Gibbs free energy as the number of particles times an intensive quantity, which is in fact the chemical potential expressed as a function of temperature and pressure. And if there are many species, or particle types, then we can write it as a sum over species, number of particles of type I, times chemical potential for species I, which depends on temperature and pressure, and also scale-independent ratios of numbers of particles of different types, like the ratio of particles of type J to particles of type K. We talked about chemical reactions and chemical equilibrium. We said a chemical equation can be put in the form the sum over species of some quantity times label for species equals 0. And that means in chemical equilibrium, the requirement that the Gibbs free energy is at its minimum subject to the constraint on the different numbers of particles for the different species, which is imposed by the chemical equation, can be written as the sum over species chemical potential of species I times quantity species I is equal to 0. Then we talked about the good old classical ideal gas yet again as an example. But in contrast to our earlier discussions, we considered it a molecular ideal gas where the molecule has internal degrees of freedom. And we saw in that case we can write the chemical potential as tau times the log of concentration divided by quantum concentration, which is what we had before, but with a new factor multiplying the quantum concentration, which I called the internal partition function. The internal partition function is just a sum over all the states of the molecule Boltzmann factor, which includes a factor of e to the minus, what we call the ground state energy of the molecule, the energy that it has when it's not vibrationally or rotationally excited. And it's important to keep track of that zero of energy because it may be different for different molecules, because there can be binding energy that changes in a chemical reaction. But then, in addition, we have to sum over the vibrational and rotational degrees of freedom for the molecule. So we get, and that factorizes into a sum over vibrational states and times a sum over rotational states, and a corresponding partition function for each. So, if we consider a chemical reaction in which all of the species are molecular ideal gases, then the condition for chemical equilibrium can be written as 0 equals the sum over I, nu I, determined by the chemical reaction, times the chemical potential, which I can write as the log of the concentration of species I minus the log of some constant independent of concentration, but depending on the species, whereby Ci, I just mean, as I read off from this expression for the chemical potential, the quantum concentration of that species times its internal partition function. So putting the log to the Ci on the other side and exponentiating both sides, the product over species, concentration of species I raised to the power nu I, determined by the chemical reaction in question, is equal to the product over species of Ci raised to the nu I, which is some function depending on temperature. I'll call it K of tau. So that's the law of mass action, which governs the equilibrium concentrations in a chemical reaction where all the species can be treated as ideal gases. But really, to derive what we needed was that the chemical potential goes like the log of the concentration, which is true in, at least to a very good approximation, in more general settings, like in the case of a solute in a solution that's dilute. So what do I mean by Z vibration, Z rotation? Well, suppose we were talking about a diatomic molecule, which we can think of as two atoms with some interaction between them. So there's some potential that depends on the separation between the atoms, and in that potential the molecule can vibrate. The frequency of vibration, the circular frequency of vibration, is let's say omega, and so the vibrational energy states are just the energy states of a harmonic oscillator with that circular frequency. So there's a vibrational quantum number which can take any value from 0 to infinity, any integer value, and the energy is n bar omega. So at least for the diatomic molecule, the vibrational partition function is just the sum over all those vibrational levels from 0 to infinity of e to the n h bar omega over tau, which is just a geometric series, 1 over 1 minus, how about a minus sign there? That's better. Boltzmann factor. E to the minus h bar omega over tau. So when the temperature is low, then this exponential is really small, and it's essentially 1. And when the temperature is high, I can expand the exponential, and it becomes in the denominator h bar over tau. So this is the small temperature limit, where small means temperature small compared to the vibrational energy level spacing h bar omega. And I'd have tau over h bar omega in the high temperature limit, tau large compared to h bar omega. So when the temperature is small compared to the vibrational energy level spacing, we say the vibrations freeze out. The vibrational partition function becomes just 1. We can think of the molecule as being in its vibrational ground state with high probability. Yeah.
Is that a C?
Boy, it sure looks like a C, doesn't it? But it really can't be, because that wouldn't make any sense. So, you know, I've often written tau over h bar c, so it just was a reflex. Right, so the vibrations freeze out at low temperature. And for the rotational partition function for the diatomic molecule, that's also fairly simple. If it's diatomic, we can think of it as a kind of a rigid rod, and it can, there are 2 rotational degrees of freedom. Since there are 2 axes perpendicular to the line connecting the 2 atoms, and it can rotate about either one of those 2 axes, rotate about either the x or the y axis. And the kinetic energy of rotation is just j squared over 2i, I equals moment of inertia. J equals angular momentum. But that angular momentum is just, as I guess you know from physics 12b, it's just an integer multiple of h bar omega. Sorry, an integer. It's just an integer multiple of h bar, rather. And so j squared over 2i would go like n squared h bar over 2i. And then for each of the rotational degrees of freedom, we would sum that over n with the Boltzmann factor. So we would get something like 2, because there are 2 rotational degrees of freedom, and the sum over the quantized angular momentum quantum number exponential of minus h bar squared over 2i tau n squared. So again, there's some characteristic spacing, although now the energies go like n squared instead of n, so that when the temperature is small compared to the spacing between the rotational ground state and the first rotational level, which has energy h bar squared over 2i, then the rotation freezes out, and the rotational partition function also becomes 1. Okay? Okay. So just to be a little bit more concrete, let's quickly discuss an example. Namely, the dissociation of molecular hydrogen. We got some hydrogen in a box, like maybe it's the universe where there's lots of hydrogen in interstellar or intergalactic space. And there's a chemical reaction. A hydrogen molecule can dissociate into 2 hydrogen atoms, or 2 hydrogen atoms can combine to give a molecule. So we can consider the reaction hydrogen plus hydrogen goes to hydrogen molecule. Or if you want to write it as a chemical equation, let's say minus 2 H plus 1 hydrogen molecule equals 0. So the law of mass action says that the concentration of hydrogen molecules divided by the concentration of hydrogen atoms squared is equal to the constant k of tau. And what is that? Well, we'll get a factor of, where was C? Right, so we're considering Ci raised to the power nu I. And so there will be a factor of quantum concentration for molecular hydrogen divided by quantum concentration for atomic hydrogen squared. And there will be a vibrational and rotational partition function factor, but only for molecular hydrogen because there are no vibrations or rotations for atomic hydrogen. And also there will be a factor coming from the binding energy of the reaction. Okay? So what that's saying is that the concentration of molecular hydrogen will, it's an exothermic reaction, right? When we combine together atomic hydrogen to get molecular hydrogen. At low temperature, the molecular hydrogen is going to be heavily favored. Or another way of saying it is if we have a lot of molecular hydrogen at low temperature, it's very hard with a thermal fluctuation to break a molecule apart into two atoms. Okay? So at low temperature, the binding energy, which I'm defining to be positive, will enhance the concentration of molecular hydrogen relative to atomic hydrogen. Okay? And since the quantum concentration is m tau over 2 pi h bar squared to the 3/2, which is proportional to the mass of the species to the 3/2, and since a hydrogen molecule has about twice the mass of a hydrogen atom, the ratio of quantum concentration of molecular hydrogen to quantum concentration of atomic hydrogen is just a factor of 2 to the 3/2 coming from the mass to the 3/2. So I can write our expression for K as that factor of 2 to the 3/2, vibrational partition function, rotational partition function for molecular hydrogen divided by quantum concentration for atomic hydrogen times that binding energy factor. So like I said, this factor will mean molecular hydrogen favored at low temperature. So if we want to find the equilibrium concentration, suppose I do have a box, and there are both hydrogen molecules and hydrogen atoms inside the box. They're in equilibrium with one another, but there's some fixed number of protons per unit volume. The protons can either be dissociated in hydrogen atoms or combined together in hydrogen molecules. So the concentration of hydrogen atoms plus 2 times the concentration of hydrogen molecules, because there are 2 protons in the hydrogen molecule, is equal to some specified constant. That's the concentration of protons, or number of protons, per unit volume. And so I have a set of simultaneous equations for H and H2 concentration, the law of mass action, and this equation, which I can solve simultaneously. It becomes just a quadratic equation for H if I eliminate H2, because the law of mass action says that our constant K times the concentration of hydrogen atoms squared minus the concentration of hydrogen molecules is equal to 0. But for the concentration of hydrogen molecules, I can use from this equation 1/2 the concentration of hydrogen atoms minus C. So the equation that we can solve to find the concentration of hydrogen atoms is just K times concentration of hydrogen atoms squared minus 1/2 concentration of H minus 1/2 C is equal to 0. Wait a minute.
It's 1/2 C.
Right, this is, oh, I see. I have the, this was, minus 1/2, no, I guess that's right. K H squared minus 1/2 H. Why do I say it's minus 1/2 C? Okay, that's equal to minus 1/2 minus C. Oh, okay, yeah, no. I guess I just have to, I should get rid of the parentheses, right? No, that's not right. 1/2 So, okay. So H2 concentration is 1/2 C minus hydrogen concentration. And so so this is actually a plus sign and this is a minus sign. That's right. Okay, so then I can just solve the quadratic equation and find the concentration of hydrogen atoms, which will, by the quadratic formula, be 1/2K minus 1/2 plus or minus the square root of 1/4 plus 2Kc. Or if I factor out 1/2 of both factors, I can write it as 1/4K. And then the solution that we're going to want is the one that has a positive concentration. So that'll be the square root multiplying through here by 4, 1 plus 8Kc minus 1 inside the parentheses. So just to check that we didn't make a mistake, we can consider the limit of a low and high temperature or low and high concentration. At low density, or low density means that C, which is the concentration of protons, is small, well, that means I can take Kc to be much less than 1, and then I can expand the square root as 1 plus 4 Kc plus higher order. So then when I divide by 4k, it's just approximately C. So low density means we have very little molecular hydrogen. It's almost all atomic hydrogen. And but if we want to find the amount of molecular hydrogen, we can go back to the law of mass action. And say the amount of molecular hydrogen normalized by the amount of atomic hydrogen, which is much bigger, is just K times the concentration of atomic hydrogen, but that's approximately C, so that's approximately Kc, which of course is small compared to 1. So the hydrogen is almost all dissociated, but of course low density also means sufficiently high temperature because the constant K has this exponential in it, which is going to become large when the temperature gets small enough compared to the binding energy. So then we cross over into the high density region. And in that case, the Kc is large compared to 1. And so this is essentially the square root of 8 Kc. And so for the abundance of atomic hydrogen, I would get the square root of C over 2K. And that makes sense now because in the high density limit, which corresponds to low temperature, almost all of the protons are going to be tied up in the hydrogen molecules. And so h squared, which is equal to 1 over k times the abundance of hydrogen, well, this will be approximately C over 2. If there's very little atomic hydrogen, it's almost all in the molecules. And so the concentration of molecular hydrogen is 1/2 the concentration of protons, since there are 2 protons in each molecule. And so H goes like the square root of C over 2K. So everything makes sense. And I guess the important lesson was that, first of all, we have all the information we need to find the concentration, and that at low temperature, the binding energy becomes the dominant factor that determines the concentration. Okay. Now let's start a new topic. Phase transitions. Okay, so this is a very active subject in modern physics, and one which will occupy us for much of the rest of the term. generally speaking, when we speak of a phase transition, we have in mind that some small change in a system variable like, for example, the temperature, it could be something else, results in some large qualitative change in the equilibrium state of the system. So, one well-known example is the three phases of water. If I consider varying the temperature, and let's say I'm considering water at 1 atmosphere pressure, then there are two phase transitions, one at 0 degrees C, one at 100 degrees C. Below 0 degrees C, the water is solid, it's ice. Between 0 and 100, it's liquid water. Above 100 degrees, it's steam. So as we increase the temperature starting below 0 degrees Celsius, there will be two phase transitions at these two special values of the temperature, 0 and 100 degrees. So we can say that water has three phases, and there are special temperatures where a transition occurs where the equilibrium state is qualitatively different, just above, say, 0 degrees, and below. Below, ice is a crystal, which has a regular order in the arrangement of the atoms. Above 0 degrees, it's a liquid, where the atoms are, or molecules, are tumbling around in random positions. But there are many, many types of phase transitions, which are of interest to physicists. So one which we kind of talked about and which we'll discuss in more detail later on is ferromagnetism. Now you know that iron magnetizes at least at sufficiently low temperature. But if I consider iron as a function of temperature, at a sufficiently low temperature it spontaneously magnetizes. It has a magnetic moment. The spins in the iron like to align. But there's some critical value of the temperature such that above the temperature the iron is, well, I'll just say, not magnetized. It has no spontaneous magnetic moment. Rather, because of thermal fluctuations, the spins are pointing in different directions. And there's no bulk magnetic moment. We talked about a superfluid. That's a phase transition too. We know at atmospheric pressure that there's a critical temperature at 2.17 degrees K. Below that temperature, helium-4 is a superfluid. And it flows without any viscosity. But above that temperature, it's just a normal fluid, which does resist flow. And there's some qualitative change that occurs at that special temperature. Another example is a liquid crystal, like the kind you have in your computer display or watch. At sufficiently low temperature, below some critical value of the temperature, there is orientational order. What it means is that the molecules in the liquid crystal, which are long, thin molecules, tend to line up in a common direction. They have a preferred axis in space that they line up with. But above the critical temperature, they don't. So they point in different random directions. Another example is the transition between a conductor and an insulator. In this case, we might consider varying the doping in a material. That is, we introduce some impurities, and the fraction of the atoms which are impurity atoms varies. When the material is sufficiently pure, when the doping is low, it's a metal. It conducts electricity. But above some critical value, it becomes an insulator. And electric current can't flow through it. Okay, all of these are examples of phase transitions. There are hundreds of phase transitions known, many of them actively studied by condensed matter physicists today. So when I say that there's some big qualitative change, what I typically mean is that there's some physical observable, something we can measure, which changes discontinuously. Well, not all phase transition. Well, yeah, I guess it's a fair statement. There's some observable quantity that changes discontinuously at the phase transition. So mathematically, we can get all of the information about what phase the system is in by studying its partition function, the sum over states of e to the minus energy of state over tau. And phase transitions correspond to discontinuities in derivatives of the partition function. Not necessarily first derivatives, maybe higher derivatives. Since physical quantities like the compressibility of the system, or its thermal conductivity, its heat capacity, and so on, these quantities can be extracted by taking a sufficient number of derivatives of the log of the partition function. Now, since it's just a sum of functions which are obviously smooth and non-singular, strictly speaking, the only way we can get a phase transition is by considering the limit of an infinite system where it's possible for singularities to arise in this sum. So, just as an aside, strictly speaking, such discontinuities, or phase transitions, arise only in the limit system size going to infinity. And since no laboratory physicist studies an infinite system, we only study finite systems. Technically, we never really see phase transitions. In practice, this distinction isn't very important because the systems that we do study typically have a large number, of order Avogadro's number, in many cases, of particles. So the some quantity of interest, for example, it could be the entropy per particle, may have discontinuous behavior as I vary the temperature, for example, formally in the thermodynamic limit, make a sharp jump. What happens for any finite system is that this discontinuous jump gets rounded out a little bit. It becomes smooth. The corners are not completely sharp, it's slightly rounded. But when there are Avogadro's number of atoms, nobody can really see the difference. So it looks like a discontinuity when you study your data.
Is that sigma?
Yeah, that's entropy.
Okay. What does it have to do with the partition function?
Well, the partition function its log is the free energy, except for a factor of temperature. We can obtain the entropy by differentiating the free energy with respect to the temperature. I'll discuss this more in a minute. And so quantities like the entropy, the pressure, other observables can be related to derivatives of the partition function or of logs of the partition function. Okay. So there are a lot of things to study concerning phase transitions, but there are two main issues. One is we'd like to understand phase transitions in kind of a general way. What are the properties that follow from general principles? And don't depend so much on the microscopic details of the material or system we're studying. So we usually speak of universal properties. The properties of the phase transition that are shared by many different phase transitions, many different materials, many different kinds of discontinuous behavior. That's what I mean by universal. So things that don't depend on microscopic details. But you might also be interested in the things that do depend on microscopic details, like, for example, maybe you have a formula for the Hamiltonian of water, and you'd like to compute from first principles the temperature at 1 atmosphere pressure at which water freezes. Well, that's the second type of issue. I guess I have room to write it up here. Sometimes we're interested in things that do rely on some understanding of the microscopic properties of the system. I'll call that properties from a microscopic viewpoint. For example, what is the critical temperature, tau sub c for critical, computed from first principles. In other words, can we, in the case of water, based on some description of the material microscopically, that it's made of hydrogen and oxygen with given chemical interactions, can we compute the temperature at which it freezes or boils? Well, this type of discontinuous behavior, it means when there's a phase transition, a system can change from one type of state to another type of state, like ice can melt. It can change from a solid crystal to a liquid, which means there are values of external parameters for which two phases can coexist. So one of the things we might want to understand is what are the properties of coexistence curves when we consider varying some parameters. So specifically, let's talk about water. Let's consider a phase diagram of water, describing the different phases it can be in as a function of, say, pressure and temperature. Well, the diagram looks kind of like this. let's say this is 1 atmosphere pressure. So if we consider with that fixed pressure, the pressure in the lab, varying the temperature, there will be 3 phases: the solid, ice, the liquid, water, the gas, steam. So at 1 atmosphere pressure, as we increase the temperature, we'll encounter 2 phase transitions, where ice melts and when water boils. And actually, if you continue to increase the pressure, a lot of complicated stuff happens up here. Ice has a lot of different solid phases under higher and higher pressure. But at pressures that are typically accessible, there are just the 3 phases to consider: the ice, water, and steam. Of course, there's nothing special about 1 atmosphere other than that's the pressure at sea level on Earth. But there are a couple of points in the diagram that are special. Well, actually, before I get to that, what do these curves represent? They represent values of the temperature and pressure where 2 phases can be in stable equilibrium with one another. Well, that's what I mean by coexistence. So if you're at 1 atmosphere pressure and 0 degrees Celsius, you can have water and ice in contact with one another in a stable configuration, a mixed phase. Water and ice in contact with one another in stable equilibrium. And similarly, at 100 degrees Celsius, we can have water and steam in stable equilibrium with one another. At 1 atmosphere pressure. But there are these 2 points that are special. Here we actually have 3 phases which can all coexist. We can have, at a particular pressure and temperature, ice, water, and steam all in stable equilibrium in contact with one another. And that occurs at one particular temperature. In degrees Kelvin, it's 273.16, and at a pressure, which is 4.58 millimeters of mercury, much less than atmospheric pressure. And there's another special point, which is up here. This one is called the triple point, because there are 3 phases all in equilibrium. This one is called the critical point. It too occurs at one particular value of the temperature and pressure, 647 degrees K and 218 atmospheres. Its significance is this: if the pressure is less than 218 atmospheres, and with that fixed pressure we consider increasing the temperature, we will encounter 2 phase transitions, first from ice to water, and then water will boil later on and become steam. If the pressure is above 218 degrees, then there will just be 1 transition. There will be no discontinuous change from water to steam. It will just change smoothly as we increase the temperature from a fluid that you might want to call water to a fluid you might want to call steam. But there's no sharp transition between the 2. The transition between the solid and the liquid never goes away, even at very high pressure. And like I said, things get kind of complicated once the pressure gets high enough. But this line keeps going. This one ends. Yeah?
Did they derive these or find them from experiments?
Well, they were originally found in experiments. And one of the central goals of many body physics over the last 4 or 5 decades, 4 decades, has been to understand this stuff, why it happens. And that's what we're going to be talking about. Okay? Okay. Now, it's also useful to think about phase transitions in a somewhat different way. just by plotting things differently. And that is, I can consider the pressure volume plane and draw isotherms in it, describing how the pressure changes as we reduce the volume at a fixed temperature. So when the pressure is high, we get behavior which is pretty close to ideal gas behavior, for which the pressure goes like 1 over volume at a fixed temperature. So this is supposed to be an isotherm. Now we lower the temperature, draw other isotherms, and eventually we get to kind of a critical isotherm in which at one particular point there's an inflection point where the pressure as a function of the volume goes to zero slope, zero first derivative, and then it continues like that. And then this special point opens up a region in which the phase coexistence occurs between liquid and water in particular, between liquid and gas in particular. Forget about the solid for now. So what happens is, as we at some fixed temperature increase the pressure, for a while, as the volume changes, the pressure stays fixed, remains constant, and then starts to decline again. So these isotherms are flat in this region, which I've marked off with the upside down U, and look kind of like that. Okay, so larger volume means we're in the gas phase. Okay, as we decrease the volume, eventually we get to the point where the pressure locks in, and as we continue to decrease the volume, the pressure stays fixed until we finally converted all of the gas to liquid, and then as we decrease the volume further, the pressure shoots up. So the volume is high. Let's say I have some piston. I'm considering some fixed temperature, tau. The volume is big. I've got just gas. Keep pressing down, and eventually liquid forms. And there will be a boundary between liquid at the bottom of the beaker and vapor above it. And the pressure of that vapor stays constant. It's in stable equilibrium with the liquid until finally I've converted all the vapor to liquid. And there's nothing but liquid here. And then if I try to compress further, the pressure shoots up because the liquid is highly incompressible. Okay? So this is just describing the same thing. We start out with a large volume chamber. It's a gas. We compress it for a while. Eventually the liquid forms. And so in here, this is the coexistence of gas and liquid. Keep squeezing down. Eventually we've converted all the gas to liquid, and then compressing further makes the pressure shoot up. So when we have coexistence, it means that we have gas and liquid in equilibrium with one another. So in in this case, we're talking about gas and liquid. In thermal, mechanical, and diffusive equilibrium, the gas and the liquid are at the same temperature, if not, there would be heat flow from the hotter phase to the lower phase. Okay, so in equilibrium, they have the same temperature. So no heat flow because they're at the same temperature. They're in mechanical equilibrium, they have the same pressure. If the pressure of the liquid, when the liquid and gas coexist, if the pressure of the liquid and the gas didn't match, then the boundary between gas and liquid would move. If the pressure of the liquid were higher, it would be pushed up, right? So they come to mechanical equilibrium where the liquid and the gas have the same pressure. And they also have the same chemical potential. If they didn't, then particles would move from higher chemical potential to lower chemical potential to find a more probable configuration. So if the chemical potential of the liquid were higher, that would mean more of the liquid would want to convert to gas until the diffusive equilibrium is established and the chemical potentials match. So when we have phase coexistence, it means that you can think of the chemical potential as a function of temperature and pressure because both phases have the same temperature and pressure, and the chemical potentials match. So there is a condition for coexistence of two phases coming from that requirement of diffusive equilibrium. Namely, the chemical potential of the liquid as a function of temperature and pressure matches the chemical potential of the gas as a function of temperature and pressure. So that's one condition on the two variables, temperature and pressure, and that condition will be satisfied generically on some one-dimensional curve in this two-dimensional space. Yeah.
Would it be the pressure at the surface of the fluid? It's like you have a...
Oh, you mean because of gravity?
Yeah.
Yeah. Well, that's true. If it were a, if it were 10 meters deep, the pressure would be higher at the bottom than at the top because of, in order to maintain static equilibrium in the fluid. So you're right. I mean, strictly speaking, gravity isn't an important part of the story. If I didn't have gravity, then I would have a little droplet. Then we'd have to take into account surface tension, which is another part of the story that we don't really need to discuss at this point. But we would have, balls of fluid, and they'd be balls because of surface tension, which would be surrounded by gas, and at the surface, the pressure would match. Yeah. Okay. Okay, so that means we can find how the coexistence curve varies in the temperature-pressure plane by considering that when we change the temperature a little bit, then we have to change the pressure accordingly so as to maintain the diffusive equilibrium. Now this determines the coexistence curve. So let's ask the question, when we consider the pressure-temperature plane, there's some coexistence curve. There's liquid on one side, gas on the other. Look at some particular point, and I'd like to know what the slope of the curve is at that point. So I consider the chemical potential at a slightly different temperature and pressure, say tau plus d tau, p plus dp, and that has to continue to match the chemical potential of the gas, okay? And I can subtract away from both sides the chemical potential at temperature tau and pressure P. And those are equal to. And let's expand to first order in small quantities to see how the change in the temperature and the change in pressure are related. So I can say that the derivative of chemical potential, I'll write sub L for liquid, with respect to pressure at constant temperature, d pressure, plus partial derivative of chemical potential of the liquid with respect to temperature at constant pressure, d tau, equals the corresponding quantity for the gas, partial derivative of chemical potential with respect to pressure of gas at constant temperature, dp, plus partial derivative of chemical potential of gas with respect to temperature at constant pressure, d tau. Those have to be equal. So if I put the terms proportional to d tau on both sides, I can write that as partial derivative of chemical potential of liquid with respect to tau at constant pressure minus partial derivative of chemical potential of gas with respect to tau at constant pressure. That quantity multiplying d tau matches partial derivative of chemical potential of gas with respect to pressure at constant tau minus partial derivative of chemical potential of liquid with respect to pressure at constant tau, all that multiplying dp on the other side. So I put, see the minus sign is different because I moved this term and subtracted away this term, put that on the left-hand side, then took this term, derivative of chemical potential of the gas, minus this term, dp, put that on the right-hand side. So that tells us what dp d tau has to be along the coexistence curve. In other words, it tells us the tangent. Yeah?
Wait, if u sub L is always equal to u sub, well, if u sub L is equal to u sub g at that point, then aren't both sides 0?
Well, these are the derivatives, right? So the derivatives aren't necessarily equal.
Like the derivative of the sum is the sum of the derivatives, so that's d tau of UL minus UG. The temperature and pressure vary. Both chemical potentials vary as a function of tau and p. So as I move along this curve, both are changing, but they're remaining equal. Right. Okay. So under phase coexistence, just dividing by d tau and putting this in the denominator on the other side, derivative of chemical potential of liquid with respect to temperature at constant pressure minus derivative of chemical potential of gas with respect to temperature at constant pressure in the numerator, chemical potential of gas differentiated with respect to pressure at constant temperature minus chemical potential of liquid
differentiated with respect to pressure at constant temperature in the denominator. Okay, so now what are these quantities? Well, we know what they are from the thermodynamic identity. Satisfied by Gibbs free energy. So we have one species here, let's say water molecules, which can be in either the gas or the liquid phase. The Gibbs free energy is a function of temperature, pressure, and particle number. We know it can be written as particle number times chemical potential, depending just on temperature and pressure. The thermodynamic identity told us that if we differentiate the Gibbs free energy with respect to pressure with temperature and particle number fixed, that's equal to the volume. And derivative of chemical potential with respect to temperature with pressure and number of particles fixed is equal to minus entropy. So when I differentiate the chemical potential, it's just, since we're keeping n fixed in both cases, 1 over n times the derivative of the Gibbs free energy. So if I define little v as v over n, the volume per particle, and I define little s as sigma over n, the entropy per particle, then our expression for the slope of the coexistence curve, dp dt along the coexistence curve, is equal to the difference between entropy per particle in the gas and entropy per particle in the liquid. Because of the minus sign in sigma equals minus derivative of g with respect to tau, the sign here got flipped. And then here I'll have the volume per particle in the gas minus the volume per particle in the liquid in the denominator. So what's the interpretation of the change when you go from the gas to the liquid phase of the entropy per particle? Well, if you want to convert the liquid to gas, you have to add heat, right, to boil it. And the heat added per particle call that the latent heat of the transition, is the temperature times the entropy per particle in the gas minus the entropy per particle in the liquid. Right? That's the amount of heat we have to add, tau times the change in entropy, to turn the liquid into a gas. So when we boil the liquid, this latent heat is positive. It's the heat that we have to add. So I can write dp d tau along the coexistence curve as a latent heat divided by temperature times delta V, the change in volume per particle. So the sign convention is clear. I should just continue to call it V gas, volume per particle of gas minus volume per particle of liquid. Okay. So this is called the Clausius-Clapeyron equation. It's an example of a property of a phase transition which doesn't depend on the microscopic details. No matter what phase transition I'm talking about between, say, gas and liquid, and the exact way the pressure varies as a function of temperature will depend on those details, we can relate the slope of the coexistence curve, which is experimentally observable, to these other experimentally observable quantities, essentially the difference in density between the gas and the liquid that coexist with one another, which determines the volume per particle, and the latent heat, the amount of heat I have to add to boil the liquid to turn it into a gas. And it's well satisfied when compared to experimental data. Actually, we can apply the same equation to coexistence of the solid and the liquid as well. So coming back to this phase diagram, which I guess I just erased, there's a triple point, and there's a liquid-gas coexistence curve which terminates at a critical point. We have gas here, liquid here, and solid here. Now I've drawn the coexistence curve between the ice and liquid water as having a negative slope, a negative dp d tau. Let's see, does that make sense? So now we're talking about delta S, the difference between the entropy of the liquid and the entropy of the solid, namely ice. Now, is that positive or negative? Right, we have to add heat to melt ice, right? So it's positive. And if I consider the volume per particle difference between the liquid and the solid, is that positive or negative?
It's negative.
How do you know?
It's water weird. Ice water expands, but it freezes.
Right, so it's actually negative. You'd know that if you saw Titanic, right? Remember what happened to Leo and Kate? Because the iceberg was floating on the ocean. Ice floats. So it actually has a lower density than the liquid. And so the volume per particle of the liquid is smaller than the volume per particle of the ice, and the difference is negative. So that's why dp d tau is negative for the coexistence of liquid and ice, although it's positive for coexistence of liquid and gas. Most phase transitions of this type have a positive coexistence curve. As you said, ice is weird. It's unusual for the lower temperature phase to have lower density than the higher temperature phase. Of course, what it means is that if I consider sitting on the coexistence curve and then pressing down on the ice to increase the pressure, that lowers the melting temperature, so increasing the pressure will actually convert ice to water, which means we can do what?
Ice skate.
We can ice skate, right. When the blade of your skate is pressing down on the water, it melts the water, so you can slide on it. So that this is positive and this is negative means that dp d tau along the coexistence between ice and water is less than 0. Okay, well, I got 5 minutes. Let me start talking about the van der Waals equation of state. This is kind of a crude model, and it's not one that we should take seriously quantitatively, but it's a useful illustration of how non-ideal behavior of a gas can lead to condensation of the gas to form a liquid. An ideal gas doesn't liquefy, right? It's an ideal gas. So if it's ideal, you have pressure volume equals n tau, no matter how much we compress or cool the gas, at any non-zero temperature, it's still a gas. So what's going to make a gas liquefy? What do we have to include that we haven't included in the ideal gas? What makes, when you cool a gas, what makes it want to form a liquid? All these molecules are dancing around, and then something makes them clump together. Well, they have to interact, right? So if we expect to have a model in which we can see a gas at sufficiently low temperature or high pressure liquefy, then we have to include in our model interactions among the molecules. So for a liquid to form, molecules must interact. And we'll use a very crude description of the effect of the interactions among the molecules. We'll consider an interaction potential between pairs of molecules, where this is the potential energy as a function of separation between molecules. Which looks something like this. Well, I'll make it actually a vertical line. So we'll suppose that there's a hardcore interaction. When you try to push molecules very close together, they bump into one another and you can't squeeze them anymore. So there is a hardcore repulsion at short distance. So we can't compress the molecules indefinitely. Eventually they're pressing up against one another. But if we want a liquid to form, we'll have to have some kind of long distance attraction, which will make the molecules want to come together in clumps. And that's what this is. A long distance attraction between distantly separated molecules. There's a potential energy which is negative and has a positive slope. So that corresponds to a force that wants to bring them together. And to model the effect of the hard core, I'll just say there's some excluded volume. Around each molecule, there's a region of some finite fixed size where the other molecules can't go. So in effect, the volume which is available to each particle is the total volume minus a volume which is proportional to the number of particles. We'll say that volume little b is occupied by each one of the particles. So each particle really only has the total volume v minus the excluded volume where the other particles are, n over b. Or sorry, n times b. I mean, I could have said n minus 1 times b, but n is enormous. I don't care about the difference between
n and n minus 1. And then there will be a new contribution to the energy coming from the long-distance attraction. Internal energy will include delta U, and then a sum over all pairs of particles. I and j are labels for the particles. ij in brackets means a particular pair. Actually, why don't I just sum over all the particles, and then I'll put in a 1/2 so I don't overcount the pairs. And I'll say 1/2 then times, I'll say sum over pairs. The potential energy of the pair, which depends on the positions of the particles labeled by I and j. But I'll consider the gas to be uniformly distributed like a fluid, so I can write the potential energy as 1/2, an integral over position of the two particles, the concentration of particles per unit volume at x and at y, times the potential energy between x and y. Furthermore, in a kind of crude approximation, I'll ignore the fluctuations in the density. We'll be adopting what we'll call mean field theory. Meaning that n of x equals n is a constant without any fluctuations. So I can just move it out of the integral and write this contribution to the internal energy as 1/2 concentration squared. Then one of these integrals just becomes an integral over all of the volume. I can change variables to say x and x minus y. So x is integrated over the whole volume. Now there's a factor of volume coming from that. And then I integrate the potential energy function over the separation between x and y. An integral d cubed x v of x. Well, that's just some number which has the dimensions of energy times volume. I'll call it, because it's negative, because this is a it's an attractive interaction, the potential energy is negative, I'll call it minus 2a, where a is some number with the appropriate dimensions. But this is a contribution to the internal energy minus a n squared over volume. B here meaning volume, not potential. Sorry about that. Where a is positive. Now it's a negative contribution to the internal energy because it's a attractive long-range interaction. So this is how we'll modify the equation of state for the ideal gas. We'll include the excluded volume factor, and we'll include the effect of the long-range attraction treated in mean field theory, and we'll see the consequences of that next time.